Hello and welcome to the continuation of fluid statics. So the next topic is going to be the measurement of pressure. And pressure measurements are done by a variety of instruments in no particular order, but we'll go from older to newer. Air pressure is measured using a barometer. There's also a Bourdon, B-O-U-R-D-O-N, tube device. Liquid measurements are often done with a piezometer, manometer, and then as a side, manometers can also be used for gas. And then the probably the more modern tools are absolute and differential pressure transducers. By all means, the more modern tools are useful for process control. These older tools still have utility as a way of producing independent checksums on the modern tools, as well as there's some applications where they actually just work better. We'll look at a barometer first. So a barometer is simply a tube that's open at one end, filled with fluid. Then we put our thumb over the top. There's a thumb. The tube is inverted and placed into a container. Of the same material. And then we remove our thumb. Pretty quickly, we're looking at now a side view. The system will look something like this. Up in this region, there'll be a slight space there, and that will be at the vapor pressure of the working fluid. So whatever the vapor pressure of the red fluid in this drawing is, that's what will be at this top end. Out here, it's going to experience atmospheric pressure. And then we're going to be able to relate atmospheric pressure to this height h. And it turns out that that relationship will be atmospheric pressure is equal to rho g h plus the vapor pressure. This is temperature dependent. And remember back earlier in the course when we were looking at the fluid properties, we had tables that showed the vapor pressure, at least of water, as a function of temperature. Generally, the vapor pressure is pretty small. Perhaps just a few percent of the atmospheric pressure. Then we have the useful property that atmospheric pressure is pretty close to rho g times h, and that's basically how your home barometers work. So barometer just means a pressure to measure a meter to measure the pressure of atmosphere. So this type of barometer is a fluid type. There's also things called barometers that are related on Bourdon tubes, and there's things called barometers that are based on pressure transducers. They're all doing the same goal, which is to find or give us a tool to estimate the atmospheric pressure, which comes in handy, especially if we're having to switch between gauge pressure and absolute pressure. Okay, so the height of rise, we could actually work ourselves out a force balance for the height of rise, not unlike what you did for the capillary tube earlier in the class. It's practically the same analysis. It's got the added term from the vapor pressure, but other than that, it's the same kind of analysis. Okay, there's some other tools that are essentially doing the same thing. So let's draw a sketch of a pipe. And if we pierce the pipe and weld on a riser tube, this is called a piezometer. And either a pipe full of water, we'll even have it flowing. And water rises up in the piezometer some distance. By convention, we assume that the piezometer, that the pressure is uniform across the pipe, and H is equal to P over rho G, or the pressure in the pipe is rho G times the height of rise in the piezometer. Another picture could be an aquifer. We have a pretty house here. Doors. Wintertime. Houses have to have a little tree in front. There's a tree. And somewhere out here in the yard, is a tube that's been pushed down underground to sample the water in the aquifer underneath the house. Now if it's a tube as I've drawn it here, and maybe the water table is right about there, this distance in the tube, yes, you can think of it as a well. It's H equals P over rho G relative to this point. So it's measuring the pressure here. If we wanted to be precise, what we're measuring in the pipe is really the pressure right there. So let me go ahead and extend my pipe down so that I'm doing it absolutely correctly. Pressure here. Now obviously in a pipe system we don't extend into the flow region because all sorts of things will clog on it. And this too could be flowing some flow rate. Bourdon tubes are similar. The entire tube deflects to detect the force differential by a change in pressure. Piezometer is a tube that's introduced into a fluid, usually a liquid. The height of rise is proportional to the pressure in the liquid. That particular pressure is called a static pressure. Wells, when they're not pumping, like we have here, are functionally piezometers. There's our pipe. There's our aquifer. Now, a related tool is called a manometer, and it's really a combination of a piezometer and some other ancillary equipment. Ancillary equipment to allow us to accurately measure pressures in things. So let's go ahead, and here we have some pipe right there. Has some flow in it, and we've attached this manometer, and I'm going to make it U-shaped. Sometimes they're slanted at an angle so that they can be read more precisely. Since this one is being hand drawn, I will make it as precise as needed. Okay, so here's a manometer. Inside the pipe, the fluid is all blue. And the blue fluid starts working its way down in the manometer, but we have filled the manometer with special green measurement fluid. Okay. So at this point right here, Pascal's law tells us that whatever the pressure is, it's identical here and here. Assume we're measuring from the center line of the pipe. We have this distance L. So there's position 1, there's position 2, and then the free surface of the green fluid is up here at position 3. And we'll call this height delta H. And what we can do now is we'll apply the concept of a static fluid moving from position 1 to position 2. Then we will go from position 2 to position 3. And when we've done that, we'll be able to relate the densities of the two different fluids in this delta H to discover what the unknown pressure at position 1. This device is called a manometer, and they are still in use today in both industrial and school application, although most control situations aren't going to use manometry. They're more of a monitoring tool. So if we were to write the hydrostatic pressure equation for pressure at point 2, it's equal to pressure at point 1, the reference pressure, plus rho, let's call the fluid blue, rho blue, G, times that length L. So the pressure has increased because we've moved down in a fluid. We go to position 2 to 3, and we have P3 is equal to whatever P2 is. And now we're moving up in a fluid, so the pressure is going to decrease. Rho, in this case it's going to be green, G delta H. Recall L and delta H are known and measured values. And so we can now substitute the various equations into each other and solve for P1, which is normally what we're after. What we'll need to know is we need to know what the densities of the fluids are, and we need to measure the L and the delta H. And then P3 would be atmospheric. And with that, we have everything we need to find the unknown at P1. So the manometers are connected to a fluid. They have their own working fluid. They measure force differential between the fluid and the atmosphere. And the devices are all assumed to measure centerline pressure, which probably in a moving fluid like I have drawn here is pretty reasonable. As with all the other devices, that force per unit area gets equated to the column height through the hydrostatic pressure equation, P over rho G equals H. So manometers are important, not so much that they're used a lot anymore. They still are used. They have value. They're certainly a pretty foolproof measurement system, although they require somebody to read them. It's kind of difficult to get a computer to read them just yet. Not impossible, but difficult. The multiple tube and multiple fluid manometers follow two simple rules. But let's first summarize manometer device for measuring pressure. It's based on a force balance between the manometer fluid and the fluid system being measured. They employ Pascal's law, and whether you move up or down in each fluid part matters. So let's make another little sketch. Maybe we have a pipe system like that, and we've got a manometer, comes out and forms a U shape, kind of a U-tube manometer. That was a terrible pun. And here's the system in here that we're trying to measure. We'll make it all blue. And somewhere in here there's an interface. Where the fluid's red. Move it up here, it makes it easier to draw. And so we can figure out the pressure at this green line is simply whatever force per unit area this column of red fluid would make. So that's H units tall. Assume at the top P equals 0 gauge. P down here is equal to rho G H. That means P here equals rho G H. And from that and knowledge of whatever this distance is, we can essentially determine the system pressure. Okay, so the two rules to follow. Any 2 points at same elevation in the same fluid, same continuous length of same fluid are at the same pressure. This is Pascal's law. Second, pressure increases with depth. So if you move down in a fluid column, actually that should be liquid. Probably true for gas, but let's be precise. Okay, let's work an example or two to illustrate these ideas. But we're going to do that on the next video.